Swayam Prabha. Digital India. Educated India.
Welcome back to Nuclear Magnetic Resonance Spectroscopy NMR problem solving session. We've had a few and we just continue with slightly bigger compounds. All right, so let's just progress from small molecules to bigger molecules, and then we'll try to do different functional groups so you get a flavor of NMR throughout the entire gamut of functional groups in organic chemistry. All right, so let's look at this. We have over here 1, 2, 3 peaks. These are blown up for you here, so you can see it's a triplet. Count the mountain peaks here. 1, 2, 3, 4, 5, 6. And it's pretty symmetric. So that's a sextet, and here's another triplet. All right, so let's look at these. So there are 3 very important pieces of data that's given on the spectra. One is the delta shift. The more electronegative the groups attached to a carbon, the more de-shielded the hydrogens are. The second one is integration. Integration or integral tells you how many hydrogens are exact same type, or pretty much how many hydrogens of that same type are on that carbon. If it's 3 hydrogens, it could be a CH3. If it's 2, it could be a CH2, and so on. The third is the splitting. The splitting is caused entirely by the neighbors. It is not caused by the hydrogens that are on the same carbon. In other words, there's no 2-bond coupling in alkanes. There's 3-bond coupling. So if you have 3-bond coupling, then the neighbors dictate what your splitting is. You don't get to dictate what it is. Your neighbors tell you how you're going to be split. Okay? So from the splitting, you can get information about the neighbors. Those are the 3 most important pieces of information that you can get from a spectra. There are others as well, but for right now, let's look at these. All right, so let's label these peaks A, B, and C, and as we have done in the past, let's tabulate the data so we can look for patterns. A, B, C are at 1.1 delta, and this is ppm, and this is 2.1 delta, and this is a delta 4.4. The second information we said was the number of hydrogens buried under each one of these identical hydrogens. So let's look at the heights here. So A, as you can see, is about 7.5 centimeters. B is 5 centimeters, and C is also 5 centimeters. You can see they're about the same height. So you have to divide this by a common denominator, and that would be, let's say, 2.5, and that is going to give you a ratio of 3 to 2 to 2. So we have 3 hydrogens, number of hydrogens, 3 of the same type, 2 and 2. That's a very important piece of information. Let's look at the third most one, the multiplicity. So A, these are all blown up for you. As you can see, it's a tall triplet, and there are 3 hydrogens, which is why it's taller than the others. This is as 1, 2, 3, 4, 5, 6 sextet, and this is a triplet. So you can see that these have the same multiplicity, and that's different. Well, from this information doesn't really give us, you can't really look at this and get anything directly from it. We need to find out what are the number of neighboring hydrogens from this information. So n plus 1 rule tells you the splitting on that. Let's call that multiplicity. So triplet. So n plus 1 triplet is 3, and so n is 2. So this A hydrogen here has 2 neighbors. It's got 3 hydrogens on that carbon with 2 neighbors. So you can think of this as CH3 is your A, that's 3 of them here, and next to that are your 2 neighbors. So these are your neighbors here. All right, so that's a pattern that you can see. Here is another triplet here, but this one has got only 2 hydrogens on it. Okay, so let's do this because let's do the triplets. So n is 2, so neighboring hydrogens are 2, and there are 2 C hydrogens that are identical, so probably on the same carbon. So there's CH2, that's your neighbor, and you next to the CH2Cs. Okay, so 2 CH2. Let's look at this, the most complicated splitting here. Sextet, that means n plus 1 is 6. That means n is 5. So you got 5 neighbors. How do you have 5 neighbors if carbon can only have 4? So basically, let's say this is CHB, and there's 2 hydrogens on it, so CH2B. Well, if you cannot put 5 hydrogens like this because maximum is 4 bonds, so that maximum is 3. So where do the other 2 neighbors go? They can be sitting on the fence, they got to be in a house next door. So 3, the overflow goes to the next carbon there. So basically what you're seeing is a CH3, CH2, a CH2, CH2, and you're seeing CH2, CH2, CH3. And how many carbons do you have for all of this? You only have 3. All right. So where are all of these situated? Well, if you look at this, obviously we have to share neighbors. So if you're sharing neighbors here, that means this CH2 is probably the same as this CH2. So now that we know who the neighbors are, let's try to figure out how we can kind of connect them. Okay, we know we need to have a CH3, a CH2, and a CH2. So both these have the same neighbors because over here you can see this is a triplet, this is a triplet. So it could be that CH3 is this is A is connected to CH2B, and that's the neighbor for this as well. So here you need to have 5 neighbors, so 3 here and 2 on the other side. Does that make sense? Let's look at it. First of all, this is taking care of the C3H7. Earlier we saw C3H7 being an isopropyl. Here is just a straight chain propyl. It's an N-propyl. So if you have isopropyl, you would have a septet doublet. N-propyl would be a triplet, sextet, triplet. So these are some trends that it's good for you to remember. Okay, so I would write this down. N-propyl would always give you will get a triplet and a sextet and a triplet. So triplet, sextet, triplet. That's the pattern for that. Then it's always going to be true. Now let's look at what the rest of the molecule is. Well, we should probably have done a omega for this, which is the unsaturation. And here you would have 2n plus 2 would be 6 plus 2, that's 8, minus and M is 7, but remember you have to take away 1 for nitrogens, add 1 for halogens, and ignore oxygens. So therefore this is going to be 6, 7 minus 1. And the whole thing divided by 2, so that's 8 minus 6 over 2 is 1. So we have 1 double bond. And we typically in a textbook you would find a list of chemical shift values for different functional groups, and you can look this up. So we know we have an NO2, and the oxygen is not in between any of this, or the nitrogen's not in between here, because that wouldn't then mess up the splitting pattern, because if you had an oxygen here, this would be a singlet and you get triplet for this. We don't have that. So therefore we don't have anything in between. This is a series by itself. You can see from this chart the nitro groups really de-shield that to somewhere between 4 and 5 here. So therefore you probably have a nitro group, and nitro groups would have to have a double bond. So that explains how you got your unsaturation of 1. So you can then put the rest of the molecule as N double bond O minus. All right. So this is something that you could figure out just by looking at your NMR. So let's look at another one. This one also has 3 carbons, but it has different hydrogens and chlorines. Let's look at the unsaturation of this one first. So here you have an omega here. That's 2n plus 2. N is 3, number of carbons, and M is the number of hydrogens. In this case, you have to add to this the chlorines, because the halogens you add 1 for each halogen. N is going to be 3 here, and M is going to be 6 plus 2. So 8 minus 8 over 2 is going to be a 0. There's no double bonds here. Let's look at the 3 most important things here. There are only 2 peaks here, A, B. So therefore you don't have 3 different environments for the 3 carbons. You only have 2, which indicates that you have some form of symmetry. That means 2 of them are identical. Okay, so therefore you have to then go in and look at well, the delta here for this is going to be 2.2 about. This is going to be about 3.7. So the second most important thing is the integration here. So if you look at that, this is about 6 and this is about 12 here. So 6 and 12, you know, is a 1 to 2. So 2 over here and 4 over here. So let's say 6 centimeters to 12 centimeters. This is A to B, divide by 6, and that's going to give you a 1 to 2, but this is 6 hydrogen, so it's 2 to 4, so they add up to 6. So then we have number of hydrogens, 2 here and 4 here. Okay, so you know that it's impossible to have CH4 because that will be like methane gas. So there's probably a lot of symmetry here. This might be just a CH2 and you have a symmetric structure for that. Let's look at the multiplicity. All right, so here we have over here 1, 2, 3, 4, 5 mountain tops. So that is a quintet. And here you only have 3. 1, 2, 3. That's a triplet. So that by itself doesn't tell us anything, but when we put it in our equation, and you can find out the number of neighbors. Okay, N is capital N is for neighbors. So here quintet is 5, so N plus 1 is 5, therefore N's got 4 neighbors. All right, so obviously they're not all on the same carbon. You can only have a maximum of 3 hydrogens on a carbon if you want to be part of a molecule. So here n plus 1 is 3, n is then going to be 2. So this guy has 2 neighbors and this guy has 4 neighbors, and that makes sense. So these are the neighbors for this and these are the neighbors for this. So that much we can get from our spectra. Now the rest is up to us where we want to put these 2 chlorines so they give you a very symmetric structure. Okay, so we can explore some. Let's see, so we can put CH3, CH2 and CH, Cl, Cl. Would this be correct? Well, if the 2 chlorines were on the same carbon, the delta value would be much higher. It would be somewhere above 5. Okay, so let's look at another possibility. Let's move the chlorine over here. CH3, CHCl, CH2Cl. This one is going to definitely have a doublet because you only have 1 neighbor. This one will also have a doublet at a different place, and we don't have 2 doublets for that. And you may have a sextet for that, and we don't have that either. So this is not going to work out either because we don't have a doublet and doublet. Well, what are the other possibilities? Well, let's see if we can then move this chlorine over here and see if that works out. CH, 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 and then I'm going to put this chlorine in a different color. A chlorine here and a chlorine here. Is this going to work out? Let's look at that. So we do have a very symmetric structure. So we have a mirror plane of symmetry. So this is exactly the same as this. You can fold these on it. So if the molecule is in a machine and it's spinning around, the magnetic field will affect all of these identically. Okay, there's no difference between them. So they will all only have 1 peak. So there are 4 hydrogens that are identical, so that's probably the B. And B has 2 neighbors, which is this. So this is B, 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 B. And the center over here is the A, and these 2 hydrogens are in a unique environment by themselves. These 2 are going to split this and this as triplets. 2 hydrogens, 2 plus 1, triplet. So therefore, this is going to be split into a triplet and triplet. So you have 4 hydrogens underneath that triplet. Now over here, if you look at this, you have 1, 2, 3, 4, and 4 plus 1 is 5. And so this is going to be your quintet, and there's 2 hydrogens underneath the quintet. So this structure pretty much explains how you would get a spectra that has only 2 peaks when you have 3 different carbons. There is a center plane of symmetry in the molecule, and that makes these 2 collapse into 1 peak. However, let's say you have a oxygen or like a ether group and a chlorine group, then you will have different delta for them, and they will have different triplets due to this, a triplet for this and a triplet for this, if you have different groups. But if you have the same groups, you have total and perfect symmetry, you would only get 1 peak for those. Okay, so NMR also takes into consideration identical hydrogens through symmetry. Let's look at the delta values and let's see if they match up. Let's see, this hydrogen is at 2.2. So 2.2, they're not next to a chlorine. They're more in the alkyl range. where you have neighboring protons that are de-shielded. If you have a chlorine here, these hydrogens are immediately impacted because they're on the same carbon, and you will get a peak, let's say between 3.6 and 3.8, and that's what we see. We have something at 3.7, right smack in the middle there. So therefore the delta also corresponds to this structure, and it makes a lot of sense. All right, so when you do an NMR, make sure every one of these would fit your structure. We'll talk to you soon. We'll come back with more structures for you. Bye. So in summary, I'd like to say that NMR plays a huge role in identifying symmetry within molecules. Here's a molecule here, 3 carbons, and all 3 of them are in unique environments. Therefore, you have 3 different peaks. Here also we have 3 carbons, however you only have 2 peaks, which means 2 of the carbons are in identical environments. If you take this, nitro is the most electron withdrawing group here, therefore it's going to pull electrons from this carbon, and these will be the most de-shielded. So the delta would be high for this. These are going to taper down because it's going through the sigma bonds. It drops off with distance, and we saw that earlier. So here this is very, very slight. This is almost in the alkane region. It's just this and this that are affected, right next door and the one next door. All right. So these are electron deficient carbons, and therefore these hydrogens are de-shielded, and the delta is going to be downfield with a higher delta ppm. They also have a different multiplicity, mainly because of this. So here are 3 hydrogens here. The neighboring carbons are 2. N is 2. Therefore, this is going to be N plus 1 is going to be a triplet, and that's what you see for your a triplet. B has got 1, 2, 3, 4, 5 neighbors. So n is 5, therefore n plus 1 is 6. That's a sextet, and you can see that over here. This guy over here has got only 2 neighbors, therefore n is 2. Therefore n plus 1 is 3. That's a triplet, and that's what you see. So the multiplicity is mainly to figure out neighbors. And the number of hydrogens, the integration here, the integral values are to figure out the number of hydrogens on that particular carbon. Once you know your neighbors and once you know how many hydrogens you have, you can pretty much create the structure. Over here you can see that, one of the ways to do a problem like this is to, come up with different scenarios and see if it matches the multiplicity. Because you have symmetry, these 2 are identical. So therefore, you are collapsing this into 1 peak, and these are unique by themselves. So this shows symmetry. And a chart like this at the back of your book would be really helpful for you to figure out whether you have 2 chlorines on 1 carbon or 1 chlorine on 1 carbon. For example, if the 2 chlorines were on the same carbon, the delta value would be much higher. It would be somewhere above 5. Okay, so you know they're on different carbons just from your delta values. So use your delta values, use your multiplicity to lay out the backbone. All right, we'll come up with more problem solving sessions for you, and until then, adios.